It's a wonderful place, and now that my talk will be done soon, I will hope to enjoy the surroundings more as well. So I will talk about the Bethe ansatz inside Calogero Sutherland models, and I guess one of the main points is that actually we do know how to do algebraic Bethe ansatz in long-range models, at least in some very specific long-range models. I will talk about long-range spin chains. I think the reason why we're blocked together is that it's both about long-range models and handwritten slides. And I should probably point out that by a long-range model, I really mean a model that interacts sort of like at all ranges simultaneously, mitigated by some potential. But it's not just sort of step-by-step kind of range. All right, so this is based on the recent paper with Didina, ongoing work with Fedor, Didina, and Gwenael, and also at the end I might say something vaguely related that is joint work with Rob Clovers. So, okay, so I want to start by motivating what I want to talk about by looking at a very well-known spin chain, which is the Heisenberg spin chain on the left, and a slightly less well-known, but still fairly well-known spin chain called the Haldane-Shastri model on the right. So they both are isotropic, so SL2 or SU2 invariant. I'll just take n spin 1/2 sides. And then generally these Hamiltonians are of this form. I don't know if the pointer, it doesn't work on the screen. Anyway, so they have this form here. So they're pairwise with a usual exchange interaction between sides I and j, as kind of written on the right, drawn on the right. And then the interactions usually become weaker at longer distances. So that's what this potential function v does. And for Heisenberg, the potential just forces you to only interact near its neighbor, whereas for Haldane-Shastri, the potential tells you that you interact with the 1/chord distance squared potential. So that's kind of nice. So you take two sides on the unit circle, and you compute their chord distance, and then 1/the square of this distance is your potential. So it's a very aesthetic pair potential, and this model turns out to be really very nice. But let me start with the left-hand side, the more traditional side. So Heisenberg model, as we all know, was found or studied because of it models magnetism. And I want to focus a little bit on the integrable structure. So for me, integrability has sort of some different things. So often people say, when they say integrable, they mean that there are a whole family of commuting Hamiltonians. So this is known for the Heisenberg. But actually really underlying this is some quantum algebra. And historically, actually, the first way that people found some hints of integrability was by exact solvability, which may or may not. So for me, exact solvability means that the spectrum can be described exactly of the model. And there are some examples which I will get to at the end, for which we know how to describe the spectrum, and we may even know how to compute higher Hamiltonians, but we do not yet know the underlying quantum algebraic structure. So for me, quantum integrability is Young-Baxter integrability. It's very algebraic, but very strong. And so for Heisenberg, it's realized in the 70s that there's an underlying Youngian structure. Actually, this is one of the main things that started the interest in Youngians and the development of this theory. And given a Youngian, you can build a transfer matrix, you can expand and get the commuting Hamiltonians, and you can then do algebraic Bethe ansatz, which is like a highest weight construction, to in principle construct the full spectrum up to solving Bethe equations. All right, so this is just to contrast with the right-hand side. So for Haldane-Shastri, this model was originally found because in some sense it's like a toy model, a lattice toy model for the fractional quantum Hall effect. So it has a very simple antiferromagnetic ground state wave function that looks a lot like what happens for the fractional quantum Hall effect. And you can also view it as some sort of lattice version of SU2 level 1 Wessel-Witten models. Was realized a bit later. So it's a nice model for different points of view. And in this case, there is a Youngian, but actually it acts by symmetries. And the reason for this is, well, you can again compute higher Hamiltonians. I will say a little bit more about this later. But of course, since the Youngian acts by symmetry, so if you have your A, B, C, D, they all commute with the Hamiltonian. So you cannot do an algebraic Bethe ansatz because you don't change the eigenvalue. So instead, you have to do some sort of trickery, and it was realized that this is related to the degenerate affine Hecke algebra, about which I will say some more later as well. And this allows you to describe the spectrum in closed form. And actually, Haldane first sort of, he had a less fancy way of seeing it, but he showed that at least some wave functions are very nice closed form, featuring some particular Jack polynomials. And so there are Youngian structures on both sides. On the left, it is kind of a structure, and it gives Hamiltonians plus its spectrum, and on the right, you have to do something else. So the game that we want to play is basically mimicking the structure that we know very well on the left inside the stuff on the right. And actually the better way of doing it is kind of generalizing a little bit both sides. So what we're going to do is, instead of Heisenberg, we're going to go to inhomogeneous Heisenberg XXX. And instead of Haldane-Shastri, we're going to spin Calogero Sutherland models, which I will introduce. So just the quick overview is that, okay, for inhomogeneous XXX, we know that basically from the algebraic Bethe ansatz, you can introduce parameters for each site, inhomogeneities, and then everything works perfectly well for algebraic Bethe ansatz. And in fact, this is already secretly a long-range model, so everybody knows how to do algebraic Bethe ansatz for at least this long-range model. On the right-hand side, now things are algebraically a little bit more clear than for Haldane-Shastri. So this model still has a Youngian symmetry. Here it's algebraically more clear how to construct the higher Hamiltonians, how to get the relation to this degenerate affine Hecke algebra, and then how to construct eigenvectors. And so what we will really be doing is mimicking the structure on the left in the setting on the right for the Calogero Sutherland model. So that's why we're doing a Bethe ansatz inside Calogero Sutherland models. And I should mention that everything that I will say generalizes to XXZ level, which is actually nicer, but it's a little bit more technical. So I decided to just talk about the XXX level. And also, it's, I think everything will generalize to higher rank as well, but not higher spin. But I'll just stay with the simple SA2 spin 1/2 case. Okay, so plan of the talk is first I will recap a bit some things from the inhomogeneous Heisenberg XXX model. Then I will tell you about the spin Calogero Sutherland model. Then I will show how to actually implement this mimicking the inhomogeneous Heisenberg structure in the spin Calogero Sutherland side. And then I will conclude with some bigger picture about long-range spin chains and some quantum many-body systems more generally. All right, so let's get started. So inhomogeneous Heisenberg XXX. So we start from an R matrix. We take the rational R matrix. It's it's a linear combination of the identity and a permutation. We construct from it the monodromy matrix, the L operator here, with inhomogeneities Zn and Z1 up to Zn at each side. And of course, we can write it as a 2x2 matrix in the auxiliary space with operators A, B, C, D, and they obey the RLL relations. So we have a representation of the Youngian. And what we usually do is we take the trace, or maybe the twisted trace, which here I just take some diagonal twist, and then we compute this twisted transfer matrix, which is just Q times the A operator plus Q inverse times the D operator. And this twist is not really important, but at the end it will be kind of nice to take some limit, so I'll include it because it's no problem anyway. And a bit more technically, the algebra generated by this transfer matrix is called the Bethe subalgebra. So it's an abelian subalgebra of the Youngian, and it contains lots of commuting operators because we can expand this transfer matrix. So let me first tell you the first version of expanding, which is close to what we normally do for Heisenberg. Namely, we want to expand at the point where at least one of these R matrices kind of becomes very simple. So what we can do is we can take our spectral parameter U to be any of the inhomogeneities. Then pictorially what happens is that, well, let me just point it out here. This R matrix, it becomes the identity or the permutation, depending if you're thinking of the R of our check matrix. And so basically this line opens up, so graphically the computation is almost trivial, and then you can write down a formula in terms of R matrix, if you prefer formulae over pictures. And all these different Gj's, of course we have n different of them, because we have n different inhomogeneities, they all commute with each other. In the homogeneous limit, so then I'm going to send all these z's to the same value, then all these R matrices here simplify a lot, and we just get this cyclic permutation operator. So in that case, it becomes a translation operator, but generally we have commuting operators. They don't have this nice property that their nth power is 1, but instead the product of all of them is, in this case, something related to the twist. If you would take 0 twist, or just q is 1, then you would get the product of all these g's is 1. So the structure looks a bit different, and we can't really think of these g's here as inhomogeneous translation operators because we broke translational invariance, but at least they deform translation operators. And maybe it's good to mention that if you take a semi-classical limit of these operators, which are sometimes called scattering operators, then you recover the Godin, rational Godin models. So that's quite an easy computation. Not field theory, just spin Godin models. Very good. So now what we do next usually, we have some sort of analogs of translation operators, is we want to go to Hamiltonians. So we just go on, we compute the logarithmic derivative of the transfer matrix at any of our inhomogeneities. Now you can do it graphically, I won't really talk you through it, but let me kind of highlight the structure of the result. It's a little bit strange looking. So what you get is a sum of n different terms. Let's start on the right, on the left actually, they're the simplest. So we have here some terms with some sort of funny rational potential function. And then here, this is pictorial language for R matrices. And then this wiggly line here, it's just the anti-symmetrizer. So what happens is the particle at Zj, it moves to I+1, then it interacts as usual, and then it moves back. But now the movement goes via R matrices. So this is a little bit strange. On the right, it's slightly more strange. If the particle that we wanted to move is to the left of the particle that we want to go to, then we have to move periodically with the twists to do this. So all the particles move to the left. Otherwise, it's the same as before. That kind of makes sense because we're on a cylinder. And now the last one is really a bit strange. So the particle Zj will also self-interact. So what happens is that this particle moves to the left until it meets itself, then it interacts with itself in the past, kind of, and then it moves back, or here it actually interacts with itself in the future. Oh, and then it moves back and ends up where it started. So it's a little bit strange, but you can write it down explicitly. You can put it in Mathematica if you like that, and you can check that they commute, which is good. So these are lots of long-range models. Of course, here, if we take, again, the homogeneous limit, then all these R matrices open up. So what you just get is nearest neighbor interactions decomposed in some sort of funny way. But it just gives back the usual Heisenberg spin chain. So these are the inhomogeneous analogs of the usual Heisenberg spin chain. For later use, it will actually be good to do something else. So what we could also do is we can take this transfer matrix and we can just do a series expansion around u is 0 or infinity. Actually infinity. Then, so here you just expand it as a series in u inverse, and then you can look at the coefficients. So here I wrote down the first few. The first is just already the quantum dimension of the auxiliary space. The second one is some sort of twisted version of the identity. I don't really know a good algebraic interpretation for it. If anybody knows, then I would be happy to learn about this. Then we get some sort of twisted version of the Casimir. So basically it's a sum over all the pairwise permutations, but twisted by our twist. So again, if somebody can tell me a little bit more about the algebraic representation theoretic structure there, I would be happy. And then we get a sum of inhomogeneities, again, sort of depending on the spin at the same site. Then we go on, so here we get some sort of something quadratic in quadratic in permutations, then some linear combination that involves the twist, the inhomogeneities, and the permutation, and then something that is just quadratic in the inhomogeneities. And you can continue this way, and it gives another set of commuting charges that will actually be a bit more convenient for our purposes. All right, very good. So here we have lots of different elements of this Bethe subalgebra generated by the transfer matrix. They all commute with each other, so now we want to simultaneously diagonalize them. Before we do it, we have to be a little bit careful, because in this context of inhomogeneities, there are some subtleties with representation theory which are important for algebraic Bethe ansatz. So a little bit more fancily, all these inhomogeneities are related to taking a tensor product of evaluation representations of the Youngian. And we always have our favorite RLL relations, which with a little bit of rewriting or using the Young-Baxter equation, you can show that if you have an L operator with inhomogeneities at some point Zi+1, then in fact you can exchange those two inhomogeneities via an R-check matrix, where R-check is just permutation times the R matrix. And this R-check is at those inhomogeneities. So this relation is sometimes called the exchange relation. It also shows up in the Knizhnik-Zavodolchikov system, sort of local condition of the KZ system. And, well, it's a nice relation, and we will use it. So it has two consequences, depending on the situation that we're in. So generically, if these Zi's obey a particular condition, then this R-check matrix here is invertible. So it means that these two L operators that only differ by swapping the inhomogeneities, they're actually similar. They're conjugate via an explicit matrix. And it can be shown that this Youngian representation now is irreducible. And the order of these inhomogeneities is not really important, right? So you can start swapping around all sorts of inhomogeneities by conjugating with R-check matrices, and you get different Youngian representations, but they're all isomorphic, so we don't really care about the difference between them. Now, in terms of I like to draw these structures of the Hilbert space. So here I have a structure of the Hilbert space for n is 4 to be precise. So what you can do is you can draw a dot for each vector in the Hilbert space. I'm going to label it by the weight, if you wish, the number of down spins from top to bottom. And then, in particular, I'm going to put on top of each other's SL2 or SU2 irreducibles. So here is the decomposition of 4 spin 1/2 sides into irreducibles in the standard way. And now the algebraic beta ansatz in this case works really well. So you start from your vector with spin up, 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 and then you use B operators to generate the full spectrum. And this, in this case, is known to be complete for these generic inhomogeneities. So everything works nice. Of course, you have to solve these inhomogeneous beta equations, which is really numerically very tricky. But okay, in principle, the model is very well understood. Now, if some of these neighboring inhomogeneities differ by plus or minus 1, then this...
In order to do that, you should have a simple choice of inhomogeneities, and the eigenvectors will be the same anyway. No?
No, because...
The eigenvectors depend on it.
The operator, right? So, and the beta ansatz equations also depend on the inhomogeneities.
Yes,
right. And something that's good while we're talking about beta ansatz equations anyway, if you know their form in the inhomogeneous case, you notice that the inhomogeneities all enter on the left and they enter symmetrically, which is kind of good, right? So the spectrum is symmetric in inhomogeneities. Right. So now in the other case, this R matrix actually is not invertible. So it's easy to see, of course, if you take this argument to be plus or minus 1, then we get the symmetrizer or anti-symmetrizer, which is up to normalization a projector, so it's certainly not invertible. And now the representation theory is a little bit more tricky. So what happens is that the representation becomes reducible, but indecomposable. And I think it's the best to think about it, look at the pictures. So what happens is either, let's start on the left. So when we take this argument to be minus 1, then what happens is that, here there's a small subspace which becomes an invariant subspace. So in this which is the image of this projector here. And this small space here, everything is fine. It's an invariant subspace. We just have a good action of the Yangian defined on it. We could do algebraic beta ansatz, no problem. And in fact, a very nice find, which is probably known, but we also found it, is that you can actually get this highest weight vector here, this the top one of the orange part, by using a B operator starting from this up, 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 usual pseudo-vacuum. And the way you do it is you take the average of the two inhomogeneities. So this is kind of nice. So in terms of the algebraic beta ansatz, what happens is that the unwanted terms vanish identically, the coefficients of them. And there's also a nice explanation in terms of the Q-cube equation, where in fact you get this coinciding roots for the Q and the Q tilde the function, if you know the story. So there's a very nice way of understanding this. But what it means is that really in this orange part, everything is described by a usual algebraic beta ansatz with some fixed roots added, which kind of reduces the size of your sort of effective spin chain. The rest here is a little bit harder. So what happens is that in here, you can still act on all the black dots with your Yangian, but the result will not just be in the black part, but it will also produce extra stuff in the orange part. So what you technically need to do is you need to quotient. You need to kill everything that was in the orange part, which you could say is okay because we already did the algebraic beta ansatz there. And then we can, in the quotient, we can still do an algebraic beta ansatz with the usual highest weight vector up, 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 up. So this is still, it's technical, but in principle, it's not too bad.
So this is the case when they fuse into singlet representation.
Yes, so because singlet here, you see that you took a small, very small, representation. Now, in the other case, it's a little bit more tricky. So what happens here is that the invariant space is the larger of the two. So really what happened is you had the two sides. You have spin 1/2, spin 1/2. Indeed, it can fuse either into a singlet or into a triplet. So here we fuse into a triplet. And so we have this bigger invariant subspace. In the bigger invariant subspace, we in particular have our favorite vector up, 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 up. So we can do algebraic beta ansatz, and we're happy. It works well. But now things start to get a bit more complicated because we cannot get out of the orange stuff because it's an invariant subspace with our Yangian. So it means that we will not be able to reach this black part starting from the orange part. So we cannot start from our favorite up, 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 up vector to go into this black part. Of course, you can still quotient by the orange to get something that is isomorphic to the black part and has a good Yangian action, but it's not so easy. I mean, it's less clean to use an algebraic beta ansatz here, so you have to really write down by hand what this vector, the highest weight vector, would be in the quotient. So here, it's a little bit more complicated, and you might say, in some sense, the algebraic beta ansatz is not complete on the right. Okay, so this is the structure of how the algebraic beta ansatz works for the inhomogeneous systems. Now, we're going to change gears. So we're going to go to the spin Calogero Sutherland model. And here, okay, so I'll start with this sort of cartoon which summarizes all the structures there. So let me talk you through it. So really what we do is we don't really start with the Youngian in this case, but we start with something called the degenerate affine Hecke algebra. I will tell you a little bit more about it later, but it's some algebra with generators and relations. It contains permutations and some operators called Dunkel operators, which kind of deform derivatives, if you wish. And these Dunkel operators and this degenerate affine Hecke algebra has long been known to be very useful if you want to understand the trigonometric Calogero Sutherland model. So these are particles that move on a circle, but they don't have any spin, like in the picture. And so here you can, in some sense, you can really describe this starting from the degenerate affine Hecke algebra, and using this formalism, you can also find its exact spectrum in closed form, and it's related to Jack polynomials, and this is an extremely beautiful story. With very explicit eigenvalues, no Bethe equations or anything like this, so it's a very neat story. Now what you can do is you can actually give these particles spins, and I will say a bit more formally what I mean by this in a moment, but let's think of this system here. So now we have particles with spins that are moving on the circle and interacting. So this can still be described by, or you can still relate this to degenerate affine Hecke algebras, and in this case, for free, due to, well, really Drinfeld, you get also an action of the Youngian. So not really all the degenerate affine Hecke algebra acts on this model, but at least the center does, and also the Youngian acts, and it turns out that this center is in fact also the center of the Youngian, which is why this model here is invariant under the Youngian, because the Hamiltonians are generated by the center of the Youngian. And now we want just to go back to the Haldane-Shastri model. So there's this particular limit called freezing. I will also say a little bit more about that later, where you, essentially what you do is you set the coupling constant to infinity, so you look at the regime with extremely strong coupling, where the kinetic energy can be, is completely dominated by the potential energy. So what's the picture, the intuitive picture of what happens is that the particles move slower and slower until they come at a halt, they sit still, and they want to do this at the classical equilibrium positions. So I'll get back to this later. And so this is intuitively how you get back to a spin chain of spins that do not move, but are nicely equally spaced, because those are the classical equilibrium positions of the Calogero Sutherland model. And now the magic is that this, if you now flip a number of down spins, then it turns out that this, well, the highest weight vector with this number of down spins are precisely related to a spinless Calogero Sutherland model with a particular, with only m, the number of down spin many particles, and a very special value of this coupling constant that I mentioned. So it means that the Haldane-Shastri spin chain has eigenvectors whose wave functions are, well, what we knew from here, namely Jack polynomials. So this is up to details. So this is a very nice story. And I hope it summarizes at least a little bit how we have, on the one hand, now we have a degenerate affine Hecke algebra, we have a Youngian, and then they kind of play together to really produce this model with all its nice symmetries. And in particular, this really explains where this structure for Haldane-Shastri comes from. Maybe it's good to briefly mention, okay, so this map here, that the one that gives from the degenerate affine Hecke algebra representation gives a Youngian action is really sometimes called the Drinfeld map, let's say, and it's a sort of an affine version of Schur-Weyl duality. And in this more technical language, there's a, you can take, actually this is cleaner at the XXZ level. What you can do is there's a duality. So Cheretnik found a relation, if you don't do degenerate, but really normal affine Hecke algebra, then there's some or really double affine Hecke algebra duality. And if you take the dual version of the degenerate affine Hecke algebra here, then it will act by just normal, what you can think of as inhomogeneities. And this same map will give the usual inhomogeneous L operator that I gave before. So the picture that I explained before, at some sense, is Daha dual or Cheretnik dual to this spin Calogero Sutherland picture. But in this case, the center is really boring because it's just symmetric functions of the inhomogeneities. So so instead we take this abelian subalgebra generated by the transfer matrix. And we have to do Alderac Bethe ansatz. And now it's kind of funny to see that here the freezing took care of equally spaced particles, and here if we think of the inhomogeneities as somehow the locations of the particles, then the homogeneous limit would kind of put them equally spaced, but that's of course more words than rigor. Okay, so this is the general picture. Now let me try to give you some details. So, okay, so what we need to do is we start from these evaluation representations. Remember, for each spin 1/2 particle, we have a parameter z, this inhomogeneity. mathematically, it's actually nice to think of this space as really spin 1/2 with a polynomial in z. So we can actually think of this z not just as numbers, but as a variable for polynomials. And this turns out to be the point of view that we will want to take. So now we can take n of such particles. So you get n spins 1/2 as well as n variables. So we get kind of like a usual spin chain together with polynomials in n variables, like there. And on this huge space, there's this representation of the degenerate affine Hecke algebra that I was mentioning. Namely, what we will want to do is basically we want to act on just the polynomial factor. So we will act by the identity of spins, and then we can swap variables, which I will denote by Sij. Or we can act on them by these Dunkel operators, which are 1/beta, this is a coupling constant, times derivatives, plus some rational functions and permutation, kind of extra crap that is good. And it gives precisely these relations that are the relations of the degenerate affine Hecke algebra. Now, this space is sort of too big. Physically, what we want to do is here, what we want to do is we want to either choose bosons or fermions for our particles. So what we want to do is we want to impose some sort of symmetry or anti-symmetry under permutation of particles. So what we define are what we call physical spaces. I will treat both the bosonic and the fermionic case in parallel. So we look at vectors for which if you exchange both the coordinates, the z's, I will often think of them as coordinates, and the spins simultaneously, then you get just a sign, like usual for bosons or fermions. And this is a subspace, and it actually really is a very nice subspace precisely because of these relations of the degenerate affine Hecke algebra, it turns out that this has a nice representation of the Youngian, each of these does. And so this is really what you get from this functor. So now we get, from the Drinfeld map, from this going from the right to the left map. So this L operator that we get now, it looks like an inhomogeneous L operator, but the inhomogeneities have to be replaced by minus or plus, depending on whether you're boson or fermion, Dunkel operators. So if you're sort of a physicist, then I think the way you want to think of this is these are like quantized inhomogeneities. We had inhomogeneities that were just commuting variables before, but now we think of them as operators instead. So we kind of take operator-valued inhomogeneities. More mathematically, what's really happening is that you use precisely this affine Schur-Weyl duality to act with the inhomogeneities on the polynomial part. And it turns out, which is non-trivial, that this L operator really preserves this subspace here. So it's a very nice property. So we can take either bosons or fermions, and we have some Youngian action. Okay, very good. So now, what is the standard thing to do? So you look at its center. So the center of the Youngian is generated by the quantum determinant of this L operator, and it is just some rational, some ratio of two symmetric functions in Dunkel operators. So essentially, what you're going to get is symmetric polynomials in these Dunkel operators, and it's well known that this is the center of this degenerate affine Hecke algebra. So your Hamiltonians can either, you can think of them as coming from the center of the Youngian or at the center of the degenerate affine Hecke algebra. The two actions coincide on these physical spaces. And then you can compute that, for instance, the sum of these Dunkel operators is just a momentum operator for the particles. And here I wrote it in additive notation, so if the z's that I've been mentioning so far are e to the I x, and then it looks as the standard way of writing momentum operator. And then if you take a sum of squares of Dunkels, then on the two subspaces you get slightly different looking Schrödinger type operators, where you have a Laplacian, and then you have a potential part, which is again our favorite, this 1/sin squares that we saw from Haldane-Shastri. But now with a coupling, this beta times beta minus or plus the permutation. So the spin dependence happens here. So here you act by derivatives, and here you act by permutations of the spins. And you need to adjust this sign here, and the signs of the inhomogeneities by your choice of bosons or fermions for everything to work well. Okay, so this is sort of the standard story. So now what we're going to do is we're going to mimic this beta ansatz business that we did for inhomogeneous Heisenberg. So what we will do is the following. So, actually, before I do this, I should explain a bit more. So this structure, these bosonic and fermionic spaces, they have an extremely neat structure. So we can characterize them very, very explicitly without beta ansatz. Just like what happened for the scalar Calogero, you get Jack polynomials, and we know exactly the eigenvalues, no beta ansatz equations. So this generalizes to the spin setting. And so what happens is that this bosonic or fermionic space, it decomposes into irreducibles with a fixed momentum and energy, which are actually the same as if the particles would not have any spins, but it has some dimension, this eigenspace, and it's in fact a Youngian irreducible. So there are lots of degeneracies. So from this point of view, what the spins really do is they produce lots and lots of degeneracies in terms of the eigenvalues of the spin Calogero Sutherland Hamiltonian. Now we can actually describe each of these irreducibles much more explicitly, and the way to think of this is we can think of this as a sort of an effective inhomogeneous Heisenberg spin chain. So for each such partition, so they're just integers which you can, without loss of generality, order to be decreasing or non-increasing, and we should have n parts. So for each of such a partition, the inhomogeneities are given by very specific combinations. So what you need to take is minus or plus, depending on whether you're boson or fermion, times this value here. So it's the lambda from your partition over beta, which was our parameter from the Dunkel operators, and then plus some little shift. And there's something, and actually this comes from non-symmetric theory, which I'm almost completely suppressing, but really these are the eigenvalues of Dunkel operators on their joint eigenbases, which are non-symmetric Jack polynomials. And to be precise, it is so if lambda was a partition, not a composition, so it should be ordered non-increasingly. Anyway, what we get from this setting is very explicit set of inhomogeneities. Now what we notice is that whenever two lambdas, so lambda I and lambda I plus 1 are adjacent, then this first part here of the inhomogeneities are the same, so you just get a minus 1 here from the j because you shifted your j 1. So this is very important for us. So what happens is that fusion will happen precisely when two parts of the partition coincide. So whenever we have a repeat in the partition, we will get fusion, and the type of fusion depends on whether you're boson or fermion. And so one thing that's extremely nice is that actually in the case that fusion appears, which is very often, this effective spin chain is precisely the invariant subspace that we had before. So we don't need to take quotients, we don't have any problems. The Bethe ansatz will work really nicely for us. So let me give two examples to make it a bit more concrete. So what do these eigenspaces look like? So one example is if our partition was strict, so there are no repeats in the partition. In this case, these inhomogeneities that we get, they're generic in the sense that we had before. So it means that we really just get a spin chain with n sides, and we can send its highest weight vector, the up vector, to a specific vector in our bosonic or fermionic space. Namely, it is essentially a Jack polynomial times the same spin vector. And more precisely, it is either the symmetric Jack polynomial for bosons or a van der Monde times a Jack polynomial with a slightly shifted parameter beta for fermions. So it's very explicit. And now we have explicit highest weight vectors from which we will be able to do our algebraic Bethe ansatz. But before we go there, let me do another example. So for fermions, actually, we don't really want to treat all the partitions in here. We want partitions which have multiplicities, at most 2. So it means the partition is allowed to have repeats, but you can only have we can only have double repeats. We cannot have 3 parts of the partition that are the same. So in this case, let me call n lambda n minus the number of these repeats in the partition. Then what happens is that our effective spin chain is just like a spin chain with only this n lambda on these sides, and it has an explicit highest weight vector that's easy to describe, and you can map it. This is a little bit more technical, but what you do is you can map this to the fermionic space by taking the same vector and then act on it with a product of our Jack matrices, which here I indicated a little bit schematically, but it doesn't really matter. It's an explicit formula which tells you how to move around the spins using our Jack matrices, depending on, so now this mu are all possible ways of rearranging the parts of the partition. So for each way of rearranging the partition, so they're often called compositions, so for each composition of lambda, we move around the downspins in this red vector using our Jack matrices, and then there's a coefficient which is a non-symmetric Jack polynomial. So maybe it's a little bit technical if you've never seen this before, but it's very explicit. Non-symmetric Jacks are very nicely characterized. There are no Bethe equations. We know explicitly eigenvalues. We know explicitly what everything looks like. So it's a really very nice setting, even if it might look a little bit intimidating if you've never seen this before. Okay. So this was old stuff. Now I want to go to kind of the new stuff. Are there any questions or comments? Or not yet?
To summarize this part, it kind of establishes an isomorphism between, on the one hand, the usual spin chain with some values of inhomogeneity, and on the other hand, with the spin Calogero Sutherland model with.
That's right. Yes, indeed.
in some fixed sector. So it has a lot of density spin, but also coordinates of particles. But it turns out you can map one to the...
Indeed. So the physical picture is that for each choice of partition here, which is each kind of energy that occurs, essentially, there will be an effective spin chain that is completely determined by your choice of partition. Indeed. And that's now precisely what we're going to use. So now I'm also happy. Very good. So now what we're going to do is, this is just a summary of everything that we had before. So now we're going to really combine these two stories that I told you. So in the way that I set it up, it's not very complicated. These G's and H's, the kind of the standards, the symmetries that I described first, they don't act on these physical spaces because I singled out a point Zi at which I did my expansion, and this is not a good thing to do if I have sort of some sort of symmetry conditions. So unfortunately they don't act, but instead you can still do this just general expansion of the transfer matrix, and in this case we get, well, here I copied some things from before where I just replaced the inhomogeneities by minus the dunkels. And essentially what you see here, so okay, here we have sort of this twisted Casimir, here we have some twisted momentum operators, so they're not so interesting yet. This is maybe a higher Casimir twisted again. Here is something that looks quadratic in Dunkel, so it's still very similar to what we had for spin Calogero Sutherland. But in this coefficient, for the first time we really see an entry that is very different from what you would get from the quantum determinant. So this is a symmetry of the Calogero Sutherland model that you get by computing a twisted transfer matrix and expanding it. And this is a symmetry, which of course, since it's generated by this transfer matrix, and whereas the inhomogeneous Calogero Hamiltonians are all generated by the center, it will certainly, this will commute with all these spin Calogero Sutherland model Hamiltonians, but it is generated by the transfer matrix, so this will not be invariant under the Youngian. So we can simultaneously diagonalize all the spin Calogero Sutherland Hamiltonians with this and higher operators that we get from the transfer matrix. And this will give a different, a new eigenbasis of the spin Calogero Sutherland model, which kind of mimics the story of the algebraic beta ansatz for inhomogeneous spin chains. And so what you do is you diagonalize per, sorry, this should have a subscript lambda. So for each of these eigenspaces, I told you that we have a nice effective inhomogeneous spin chain. We may or may not have fusion, but if there's fusion, then we just pick the nice invariant subspace, so there's no problem. We can it either contains up, 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 or we can get up, 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 up. We can get it from up, 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 up by acting with B operator at a very specific kind of fixed beta root, if you wish. And from this state, you can now act with your B operators that come from this L operator here, and basically you can mimic the whole algebraic beta ansatz. So I don't really want to go into details, but you see that everything now is set up very nicely. So we can, per eigenspace, per effective spin chain, we can do an algebraic beta ansatz, and we're nicely in the case where everything works perfectly with a complete description of the spectrum. And just a small side remark, the reason why I wanted to include this Q, the twist, is that if you take this twisted transfer matrix QA plus Q inverse D, then of course let's normalize it by dividing by Q plus Q inverse. Then we can send Q to 0 or infinity, and we pick up either the A or the D operator. And in this case, if you diagonalize the A or the D operator together with the quantum determinant, this is known as the Gelfand-Zetlin subalgebra of the Youngian, and it's also known to have a nice basis. And so what happens is that this algebraic beta ansatz here, in this limit, the beta equations become extremely simple, and you can just write down the solution. So basically, your beta roots are either inhomogeneities or 1 plus inhomogeneities, something like this, depending a little bit on whether you choose A or D. And you can plug in these explicit values of the beta roots in the algebraic beta ansatz, and you recover the Gelfand-Zetlin basis, which is what Nakamura and Uglov long ago used. So this construction, by including the twist, we also recover their way of describing the eigenbasis of spin Calogero Sutherland. But I think it's kind of a nice game, because normally, you know, you take these, you do algebraic beta ansatz, and you always start from essentially up, 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 up. So it's a little bit boring. We always say, oh, we choose a pseudo vacuum, but it's just up, 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 up. But here we really see examples where we get some sort of non-trivial pseudo vacuum vectors from which we have to start. Namely, for each choice of partition, we get some quite non-trivial vector here from which we have to start for our algebraic beta ansatz. So that's really almost all of the story. So now let me get back to spin chains. So above here is just what I had before. So now we're going to do this freezing limit. So as I mentioned before, we want to send beta, which was the coupling constant. Look here, it's sort of the constant for the potential. And we're going to send it to infinity, or really we're going to expand it, and we're going to look at the most dominant terms. So at order beta squared, we just have some constant, which is not a very nice Hamiltonian. So what do we want to do is we want to minimize it. And this is minimal precisely at the classical equilibria of the Calogero-Sutherland model, which are these equally spaced values of the variables. For the more mathematicians here, if you want to do this, of course, this specialization is not really nice because we had a kind of a setting that was very symmetric or anti-symmetric in terms of variables, and now we want to assign very non-symmetric values. So what you can do is you can take a quotient by an ideal generated by power sums, where you choose the nth power sum to be n. And this is a nice way to say we set the z's to essentially these roots of unity, but up to permutation, and we don't specify which permutation. So it's a nice and symmetric way of doing it. So you can quotient this big space by this. And then we have minimized this part, we move to the next part, and now assigning these x's to those values that we get from here, we get the Haldane-Shastry Hamiltonian, which I repeated up to some constants. So this is how you get the Haldane-Shastry Hamiltonian from the spin Calogero-Sutherland. Well, and moreover, we had an L operator, so what we can do is we can just send beta to infinity. If you look at the Dunkel operators, then beta to infinity just removes the kinetic part. So we just have something which only has this rational part and permutations. Coordinate permutations we can in principle replace by spin permutations using the bosonic or fermionic condition. And so the rational functions will be evaluated to some numerical factor by this thing here. So we really get an operator that acts on the spin chain. It commutes by this Haldane-Shastry Hamiltonian by construction. It's easy to check. And so we have constructed. This is the standard construction of the Haldane-Shastry model and its Youngian symmetries from this spin Calogero-Sutherland business. And now essentially the internal beta ansatz from before, it will still work, but there are some subtleties. So to just be brief, remember that here we have this extremely nice explicit description of eigenvectors. So in the Haldane-Shastry side, actually we don't really construct eigenvectors by first doing them for spin Calogero and then freezing, but instead we do this sort of detour. And I don't really want to go into details, but what happens at the end of the day is that you construct, again, specific or explicit eigenvectors, and they have the following form. So they're just, here's a vector with m downspins, and the wave function is given by a van der Monde polynomial squared times a very specific Jack polynomial at this value alpha star is a half. So it's called a zonal spherical symmetric function.
Can you write this as BBBB, acting on something?
In the Q case, that's more clear. So in the Q case, this looks a bit more complicated, and in fact there are check matrices here, and what they really do is it is like you have BBB here. That is kind of the Q deformation. But if you take the...
This looks more like a coordinate beta ansatz wave function. And
I agree.
you have the sum in front, so it's not about the sigma minus, but you should have a product.
I agree. So I do not know how to do it, but on the other hand, we will do the opposite. So I do not know how to write this as a BBB of something, but here we have a vector which is Youngian highest weight. It's not obvious, but it can be shown. And now we will use this to act with BBBB to generate the whole Youngian with the B operator coming from here. And then we will generate a basis for using the algebraic beta ansatz for each eigenspace of Haldane-Shastry.
Those are Youngian highest weights.
So these are the highest weight ones, indeed. So it's not completely, so I don't know. But there is some sort of factorization properties which are more manifest in the Q case. So if you send the XXZ-like case. So if you send
you want to construct from B operators, you want to construct these raising operators of the second level in the Youngian that allow you to go up
literally. So I mean, I would just use this L operator in which you put the Dunkel operators and blah blah blah, and rather than the sort of the second level Youngian, because if you use those, it's not so obvious which linear combination ones you take. Whereas here you just have a B operator, and you can just plug in values of Bethe ansatz equations. So that's what I would do. Okay, so this gives a different eigenbasis for the Haldane-Shastry spin chain, which are still eigenvectors of the spin chain, but now they're a little bit different than what one might normally do, because we used beta ansatz inside each eigenspace to construct these vectors. So I think it's kind of a cute story. So just to wrap up. So here's the same picture. So I hope, let me just repeat. So we started from the degenerate affine Hecke algebra. We had an action on a huge space, but what we could do is we could look at bosonic or fermionic subspaces, and on there we get an action of the center of the degenerate affine Hecke algebra, and we get an action of the Youngian, whose center in fact coincides with, so these two centers coincide. They give the usual spin Calogero Sutherland Hamiltonians. But now what we do is, rather than only focusing on the center, we take this intermediate stage of constructing the transfer matrix with its abelian, the abelian subalgebra. And it contains Heisenberg-like symmetries, which are symmetries of spin Calogero Sutherland, but do not commute with the Youngian, and therefore we're able to do algebraic beta ansatz. And then the upshot is that for each, depending on some conditions on the number of repeats, partition lambda, we will get an effective inhomogeneous spin chain with, whenever you have multiplicities, then there will be fusion, but luckily we always pick the invariant subspace. The algebraic beta ansatz works very nicely then, and therefore we construct a new eigenbasis for spin Calogero Sutherland, and by freezing Haldane-Shastri. So that's what we did with Didina and Feder and Gwenaël. I'm currently writing this up. And the motivation for this, at least for the two other, well, maybe the three other people, is that actually now we have constructed a setting in which you can try to understand separation of variables. So, and this is kind of quite cool because for instance, people like IPhT, they have some long-range model where you would like to understand things. In general, there's a long-range spin chain, as we've seen. I mean, this is the motivation for you too, I guess, to do this. So there's a long-range model, and one might want to try to understand its spectrum by SOV, but there's not so much known about this. So here we created a toy model where we have both algebraic beta ansatz type of structures and it's long range, so it's under very good control, and hopefully we can understand how to do SOV in here.
As far as I remember, there was a paper of probably 95 by Scrianin where he treated, I think, at least three particle Calogero-Moser by separation of variables.
Perhaps.
Yeah. But I guess here we're with spins, so it will be somehow related but different.
Yeah, it was without spins.
That's true. Yeah, that's a good point. We should have a look at that again.
At least something is known.
Yeah, that's true. Yeah. So for the others, it's motivated by ADS-CFT integrability. I really like the sort of the representation theory hiding under all this story, and I think it's very nice. And there are lots of actually things that I would like to understand better, and I think are generally not yet known. But let me zoom out a little bit and put this in the context of my more broad research interest, which is, so I've told you about the Heisenberg spin chain and the Haldane-Shastri spin chain. And in the previous talk, we already heard that there's some model called the Inazemtsev spin chain. And what it does is it's still of the form that I showed at the start, so this pairwise isotropic model, but now it has a potential which interpolates from nearest neighbor to this 1/course distance squared. And it involves specifically some elliptic function, and the imaginary period is the one allows you to tune the interaction range here. And now, of course, we know that Heisenberg has all these generalizations, which, XXZ is very easy by integrability, and then XYZ becomes much more complicated. So in the past 5 years already, I've been working on Q-deforming this Haldane-Shastri business. So this is based on work by Uglov that was essentially unnoticed, unfortunately. So he found a model which is a Q-deformation of Haldane-Shastri. He found an explicit Hamiltonian, but it's very complicated, and the paper was never published, and I think nobody knew about it. In fact, he solved Vincent Pasquier wanted to find this model, and he set up the machinery with algebraic beta, with affine Hecke algebras to do this, but he wasn't able to compute a Hamiltonian, and even Vincent didn't know that Uglov had found this model.
The paper was not published in the sense, not in the...
It's on arXiv, but it's not in a journal, that's right. And so, for some reasons, I was interested in this, and I found the paper, and I worked on it, and we were able to write it in a much nicer pairwise form. And then with Vincent and Didina, we managed to repeat this story with the affine Hecke algebras and so on to really construct its explicit eigenvectors. Again, no beta ansatz, but now McDonald polynomials, and it's a very nice story. So actually, the motivation for all of this, and that's what I want to finish on, is that long ago, during my PhD with Rob Klabbers, we knew about Inazemtsev, and actually Haldane in his first paper, he sort of says, oh, you can kind of make an XXZ-like version of Haldane-Shastri by just putting delta in the usual way in the interactions. And then he sort of said, at least in some cases it works. But it doesn't really. So it has certain properties, but it doesn't have most properties that one would want. But back then we didn't know this. So we thought, okay, if this can be XXZ kind of deformed, and here we know very well how to do it, then of course what one would like to see what the XXZ-like version of Inazemtsev is. And so we've been trying on and off for, I guess, well, for quite a while now to do this, and we have not really managed to do anything until recently. So last summer we were able to sort of guess Hamiltonians for a Q-deformed Inazemtsev spin chain, and we could check numerically that they commute. So that's very non-trivial because they involve lots of elliptic functions. They involve dynamical elliptic R matrices. So it's all very complicated. But numerically, we can check that it commutes. And we've been working quite hard since then to try to really prove this. And I think so in the last 2 weeks now, I'm happy to report that we really completed our proof. So we finally really have a proof. We have a model here and a proof of it. And really the underlying machinery is always the following. There are always these quantum many-body systems, like trigonometric Calogero Sutherland or elliptic Calogero Sutherland, or its deformations, Reichenar's McDonald type models, which also have trigonometric and elliptic versions. And if you give these models spins in the right way, then they remain integrable in the sense that you have commuting Hamiltonians. And then you can do this freezing to compute commuting Hamiltonians from them. For the spin chains. So that's really what we've been doing. And my big picture is that I would like to really do this for this sort of doubly elliptic model, which would be at the XYZ level here. This is going to be super, super complicated, so I don't know if it's possible. But if it is possible, it would really give a big spin chain, which I think would be very interesting to understand integrability, what kind of I think this, so I should maybe mention that for Inozemtsev, it is not known. This is an example where we know a description of the spectrum by a relation to scalar Calogero Sutherland, elliptic, but we do not know an L operator. And so in our case, that is in the Q-deformed case, this is still true, but at least we get a lot of handles on sort of integrable structures, and hopefully we can use this to understand the integrable structure here, which would be really nice. And I think it will really, if it would exist, such an L operator, I think it will really be a completely new type of integrability that is very different from the Heisenberg side, and also different from what I told you about for the Haldane-Shastri side. So I'm really quite excited about this. And
the Reisner's time, we heard some talks at Rakvis, right?
Right. So there's
Zotos and the postdoc who is
right. So Matushko and Zotov, they found right. So they found versions. They found models which look very much like what you want here, except that they're not the models that are here. So they do not limit to Inozemtsev, they do not limit to Q-deformed Haldane-Shastri, they do not even limit to Haldane-Shastri, and they don't actually limit to Heisenberg either. Right, so they are related to, so really what happens is, so what they do here is their elliptic Reichenar's model is constructed with Baxter-Belavin R matrices. And the way that I now start to, I think what happens is that they're doing a construction for like, the A2, the twisted A series. Whereas we are doing the construction for the untwisted A series. And at the level of the R matrix, at least for SL2, this is just a conjugation, which is not so, it's quite innocent. But at the level of these long-range spin chains and Calogero Sutherland or Reichenar's type models, these twists, it's not true that one of the dynamical model would be related to the 8-vertex type model, and therefore the spectra look completely different. So we here have lots of degeneracies. If you take their model, it's an integrable model, but it does not have all these extra degeneracies. So all this stuff about degenerate affine Hecke algebra and Youngian symmetry, this is really on the side that I'm talking now. What they do is a very interesting different type of class of models, which somehow structurally look identical, but in terms of spectrum behave very differently. And I think even in the trigonometric case, they don't know how to. In the Heisenberg case, the limit that you get here is kind of interesting. It is I think it's like an XX0, but like an XY model. So it's a sort of like like delta zero kind of version of Heisenberg XXZ. One thing that's a bit a bummer of our model is that this limit doesn't really work well. So we can't quite get Heisenberg XXZ, but instead we have some only in the isotropic limit. We really get back to the normal Heisenberg model. Here we get some deformation that we're not able to get rid of. So, but I think that's the punishment for doing more mathematical stuff, that you don't always get physics at the end. But in any case, I think it's very interesting. Thank you for your attention.
Okay, thanks a lot. Any more questions?
So first a comment, I definitely should have said the word perturbative when I said about the, but like one big difference I think when you do the anisotropic thing, in comparison with the perturbative, is that the R matrix increases the size, like the RTT doesn't give you anything different for the inhomogeneous case, I agree it's like a long-range spin chain, but the size of the R is still the same, and RTT gives you, like, the inhomogeneity doesn't affect RTT.
That's right.
But
It's not really completely long range. It's a bit.
Sorry?
It's not really long range in a way. XXX by adding homogeneity, it's kind of long range, but.
Yeah, but it's a different type of long range. But what I was wondering now is, like, your talk was very nice, and I was wondering now if there is any impediment about if you had a perturbative Youngian to try to do something similar to what you did for the perturbative case. Do you see any?
So what I believe is that what we're doing, especially with this on this trigonometric site here, is extremely, representation theoretic and delicate. I believe if you would perturb and kind of cut off, I think you will immediately destroy all the structure that we have, is what I imagine.
Okay.
So I think it will not have Youngian invariance if you just cut off in any way, really, the model. So no, I think they're really very different. I think this is extremely non-perturbative, this expression.
Okay. It's very nice, thank you.
The thing is that you don't, if you try to deform Heisenberg to Inozemtsev, you immediately lose the construction of the monodromy matrix. And you cannot do, we would have liked to do Bethe ansatz because it's interesting for any quest for superior means, to do Bethe ansatz and the separation of variables on Inozemtsev, but because of you don't have the algebraic Bethe ansatz construction, you have to go to the limit where you still have a Bethe ansatz. I mean, you still have a transfer matrix, and you can
I see.
do something exactly, yes.
Questions right now? Oh, Jeremy?
Can you maybe comment on the Daha duality, because you mentioned it in the context of relating the story with Heisenberg and how the Shastri is with Inozemtsev. Does that also fit in? Or?
Sorry, in that?
With Inozemtsev, does that?
No, in Inozemtsev. No. It's, so in terms of published literature, there's no such connection. In terms of the proof that we use to get commutativity here, so as far as I know, and as far as anybody that I've asked seems to know, there's no sort of elliptic in this sense version of the degenerate or non-degenerate affine Hecke algebra. However, it has a distinguished abelian subalgebra. Here it was the one with Dunkel operators, and here is one with Y operators. They're called Cherednik Y operators. They're like some sort of difference version of Dunkel operators. And this abelian subalgebra actually has an elliptic analog, and that's enough for us to construct these models and prove that they commute. But this is very delicate and involved to actually get this proof. But so that little part of Hecke algebra survives here. Now you might think, okay, we know the L operator. I mean, that's what I thought. We know the L operator, and we have some sort of elliptic Dunkel operator, so we can plug them in there on our bosonic or fermionic space with a sign depending. But the annoying thing is that they don't obey the relations of the degenerate affine Hecke algebra, and precisely those were the relations that I needed to show that the L operator acts on bosons or on fermions. So I can sort of produce an L operator which obeys Young-Baxter with some elliptic Dunkel operators, but it's not really, it doesn't seem to be the one that is really related to spin elliptic Calogero Sutherland. Or actually I can produce another one which is related to spin elliptic Calogero Sutherland, but it doesn't obey Young-Baxter. So it's a bit of a bummer. So the rigidity of the structure does not allow me to get the Youngian part, it only allows me to get the abelian subalgebra with Hamiltonians. That's sort of the short story.
Okay. So I see no more questions. Let's thank you again.